Hello everyone, I am Amulya, Assistant Professor in Department of Electrical and Electronics Engineering, Sai Vidya Institute of Technology. In today's session, in the module 2, I am solving the second problem on a symmetrical fault analysis. So this is the given problem. So here you can observe the generator and motor both having the same ratings of 25 MVA, 11 kilovolt and 15% subtransient reactance, and these two, generator and motor, are connected with the help of two transformers and a transmission line. So here the transformers T1 and T2 both having the rating of 25 MVA, 11 kilovolt slash 66 kilovolt and 66 kilovolt slash 11 kilovolt with a reactance of 10% each, and the transmission line is having a reactance of 10%. So here you have to consider the transmission line values, that is 25 MVA, 66 kilovolt as a base power and a base voltage. After that they have given the ratings of the load, that is on the motor side 15 megawatt, 0.8 power factor leading, and the terminal voltage is 10.6 kilovolt. So here you can observe on the motor side there is a symmetrical three-phase fault has occurs. Due to the occurrence of this fault, you need to find out the subtransient fault current at the generator, motor and also at the fault point side. So this is what the given problem is. So before solving the problem, always have a practice of writing the ratings of all the components below the single line diagram, so that it will be easy for the simplification. So first I'll write the rating of all the components below the ratings, then we'll proceed according to the step. So here I have written the ratings of all the components, and you have to observe. So here they have given the ratings on the load also. So that is understood that the given system is loaded. So from the given data itself, you need to clarify whether the system is loaded or unloaded. So now we'll proceed with the steps. Step 1, that is converting a per unit reactance diagram from a single line diagram. So before that, first we have to write the base power and a base voltage. So in the problem itself they given 25 MVA and 66 kilovolt. So this will be the base power and the base voltage of the transmission line. So now MVA base new, that is equal to 25 MVA, and kilovolt base of the transmission line, that is equal to 66 kilovolt. So now taking this as a reference value, so next what we have to do, we need to find out the base voltage of the motor and also on the generator. So you know that these two are lies on the LT section. Use the LT section, but I'll directly substitute the values of the generator and also the motor. Kilovolt base new of the generator by using the LT section, that is kilovolt base new on HT section, nothing but the transmission line 66 multiplied by low voltage rating by high voltage rating. So now observe, between the transmission line and a generator we have T1 transformer is there, low voltage is 11, high voltage is 66. So after substituting we'll get 11 kilovolt is the new value of the generator. Similarly substitute the kilovolt base new of the motor using the LT section, that is base voltage on the HT transmission line multiplied by low voltage is 11 kilovolt, high voltage is 66 kilovolt. So even for the motor also you'll get the value as 11 kilovolts. So next what we have to do, we need to calculate the per unit reactance for the generators and also for the transformers, then for the transmission line. So now look at the given data here. Generator and motor both having the same ratings. So for the per unit reactance for these two also will be same. Similarly T1 and T2 is also having the same ratings. So we'll do one single calculation. So first I'll calculate for the per unit reactance for generator 1 and 2. Generator and motor. So here I have written the formula. X per unit volt value is 0.15. MVA base new, that is step 1 25. MVA base volt, that is also 25. Kilovolt base square volt is 11 kilovolt. New value is also 11. So after substituting, we'll get the answer as 0.15 per unit. So this is the per unit reactance for generator and motor. So similarly, I'll calculate for T1 and T2. So use the same formula as you already know the steps from the first model. X per unit volt for the transformer is 0.1. MVA base new will be 25 MVA. MVA base voltage, that is also 25 MVA. Next you can calculate the kilovolt value, old and new. Consider any one side and cross check for the secondary also. If 11 kilovolt is the volt value and connected to generator means that value also will be equal to 11. Suppose 66 is the volt value means connected to transmission line, that value is 66. So both the side you will get the same answer. So after substitution you will get the answer for the transformer T1 and T2 as J 0.1 per unit. So next similarly we'll calculate for the transmission line, that is the per unit reactance of transmission line. Since the transmission line value it's already expressed in percentage, see observe here. So this transmission line is already expressed in percentage, that is a 10%. So in such a cases what you can do, already it is there in the percentage, no need of again converting into per unit. So when you have to go for the percentage conversion means when the transmission line values are given in ohms. So then only you have to convert into per unit. So here the direct answer is given. So you can mention the transmission line reactance in per unit. So here in the given problem they mention 10%. Converting into per unit means it is J 0.1 per unit, that is dividing by 100. So now finally we can draw the per unit reactance diagram from a one line diagram. So this is the reactance diagram from this one line diagram. So this completes step 1. So next we need to proceed with the step 2, that is calculation of a pre-fault voltage and also the load current calculation. So you got to know that from the given procedure this system is loaded. So if the system is loaded with these three data means, then what you have to do, you need to calculate VPF first, that is the pre-fault voltage, and after that you can calculate the load current value. So next is calculation of VPF, that is a pre-fault voltage in per unit. So I'll write the formula VPF, that is VPF actual divided by VPF base. So here VPF actual is nothing but given in the problem 10.6 kilovolt. So you can write 10.3 or need not of writing also, because both the voltages are expressed in kilovolt only. Kilovolt it get cancelled. Then V prefault base. So here one question arises. So we have three base voltages are there. One is the transmission line, generator and motor is there. So which base voltage we have to consider? So what you have to see means, since you are calculating the pre-fault voltage on the load side. Load means what it is? The motor. So that means the pre-fault voltage you have to consider the motor value only, that is 11 kilovolt. I'll repeat. So there are three base voltages are there. Which base voltage you have to consider means, so you are calculating the pre-fault voltage for the load side. So load is nothing but motor. So you have to consider the base voltage of the motor only, that is 11 kilovolt. So here you can write 11 kilovolt. So answer you will get, that is 0.963 per unit. So this is the pre-fault calculation. And after that you can go for the load current calculation, that is IL in per unit. So IL actual divided by IL base. So you know the formula for the actual calculation and also for the base. First we'll do for the actual one. So P divided by √3 V cos phi at an angle of cos inverse of phi. So now look at the given data. So this is all your actual values. 15 megawatt, 0.8 power factor leading, 10.6 kilovolt. So same we will use in the actual calculation. Power is 15 megawatt divided by √3. Voltage is 10.6 kilovolt, 10.6 into 10 power 3, and the power factor is 0.8, and at an angle of cos inverse of 0.8. Here the angle is power factor leading, so the sign will be plus. So after substituting this IL actual, we will get the answer as 10,212 at an angle of 36.86 degree ampere. So this is the answer. Next, similarly, you can calculate for the base, that is IL base. So the same formula, but there will be no power factor there. Okay. So P divided, that is P base divided by root 3 into V base. So now here also V base is nothing but you have to consider the motor value. Why? Because you are calculating the load current. Load is nothing but always the motor. So here V base of the motor only you have to take. So now look at the step 1. MVA base is a 25, 10 power 6 divided by root 3 into V base of the motor. So the motor value base voltage is 11 kilovolt. So you will get the answer for the base as 1312.5 ampere. So now you can substitute these two answers in the IL per unit formula, so that you will get the final answer as 0.778 at an angle of 36.86 degree per unit. So remember this answer. This is IL value in per unit. So this completes step 2. So next we need to find out the fault current at the 3-phase fault point. Now the step 3 is fault current calculation IF per unit by using Thevenin's theorem VTH by ZTH. So you know that VTH is nothing but VPF value in per unit. So in the last step only we have calculated the VPF value in per unit, that is 0.963. So the same answer I have written here. So next we have to find out ZTH value. So for finding the ZTH value, we need to write the same reactance diagram by neglecting the source voltage. So now observe, this is the given reactance diagram. So the same reactance I'll write by neglecting these two source voltage. So this is the reactance of the generator, transformer 1, transmission line, transformer 2, and after that we have a reactance of the motor. And here you have to indicate properly, this is the point where the 3-phase fault has occurs. So you can mention these 2 points as A, B. The reactance is 0.15, 0.15, and this is J 0.1, J 0.1, J 0.1, this is J 0.15. So how do you find out, or how do you simplify this into simplified form? Means you know that where the fault has occurs, that is been dividing into 2 networks. So all the reactances now connected are series here, and these reactances it will be parallel with the reactance of the motor. So same way I'll write. So this is the fault point AB. So this reactance of the motor is 1,5. So now observe here, adding all these 3 reactances, J 0.1, 1, J 0.1 and 1,5, we will get J 0.45. So now in order to find ZTH value, so we need to use a parallel formula, that is J 0.45 is in parallel with J 0.15. So after that we will get the ZTH value as J 0.1125 per unit. So next what you can do, you need to substitute VTH value and ZTH value in the above formula. So what you will get the answer as 8.85 at an angle of minus 90 degree per unit. So remember, this is the value for the fault current in per unit, 8.85 at an angle of minus 90 degree. So next, this is going to complete with the step 3. So next we are going to calculate with the step 4. So that is subtransient current calculation in per unit first. Before the subtransient current calculation, we know the formula for the subtransient current or the post-fault current. It is the pre-fault current plus the change in fault point, change in current at the fault point. So this is the steps we have seen in the procedure. So pre-fault is nothing but IL in per unit and change in current is nothing but I1 and I2. So that we have to find. After that we can calculate subtransient values of current. So for the calculation of a change in current, so what we have to do, the same reactance diagram we need to rewrite by connecting the Thevenin's voltage at the fault point by reversing its polarity. So now observe, so I am writing the same reactance diagram. So here we have to connect the source voltage with the reverse polarity, and here we have a motor reactance will be there. So this is a reverse polarity VTH. So this is J0.15, J0.1, J0.1, and this is also having same value. This is J0.15. So here the current flowing will be I1, current flowing will be I2. So now we need to calculate I1 and I2 separately. So now I'll write the formula. I1 is equal to VTH by all the reactances, that is J0.45. VTH value we have obtained here 0.963 divided by J0.45. We will write the final answer as 2.14 at an angle of minus 90 degree per unit. Next, similarly we'll do it for the I2. I2 is equal to VTH by only one reactance J0.15, that is equal to VTH is 0.936 divided by J0.15. So we will get the answer as 6.42 at an angle of minus 90 degree per unit. So we completed with the I1, I2 calculation. So next we will do the generator subtransient current calculation. Already you know the formula from the previous problem itself. So Ig double dash per unit will be equal to I1 plus or IL plus I1. So this IL value we calculated in the step 2 itself. So the same value we will consider here from the step 2. So directly I'll write the answer. So I calculated the final value. So observe here from the step 2, the IL per unit value is 0.778 at an angle of 36.86. This value I added with I1. So this is the final answer for the generator subtransient current in per unit. Same way I am going to substitute the motor subtransient current. So this is the answer for IM double dash in per unit minus 0.622 minus J 6.89 per unit. So this complete with the step 4. Next we are going to proceed with the actual current calculation in step 5. So in the step 5 actual current calculation, Ig double dash actual is equal to Ig double dash per unit into I base. So this is the answer from the previous step of the Ig double dash per unit. Now we have to calculate I base. The formula I'll write here, P base divided by root 3 into V base. So V base of which base voltage you have to consider means generator only we have to consider, because you are calculating actual value of the generator here. Okay. So in the previous problem we have only one base voltage is there that we have considered as a common value, but here 3 base voltages are there. So which component actual value you are calculating, so that base voltage only you have to consider. So the base power for the entire system, look at the step 1, it is 25 into 10 power 6 divided by root 3 into V base of the generator. So that is V base of the generator is 11 kilovolt. So after simplifying the answer, we will get the final value as 816.4 minus J 197 amperes. So this is for the generator actual value. So next, similarly I'll do it for the motor. So you can write the same formula. Im double dash actual will be equal to Im double dash per unit into I base. So Im value will be this value we calculated in per unit minus 0.622 into J minus 6.89 into I base. I base is P base into root 3 V base. So here also we need to take the base voltage of the motor because we are calculating the base current of the motor. So V base will be motor value only. So now P base is 25 into 10 power 6 divided by root 3 into V base of the motor. So now observe the step 1. So V base of the motor is again 11 kilovolt only. So the same answer you can consider here also, 10 power 3. So I'll write the final answer after the simplification as minus 8.816.2 minus 9041.2 amperes. So this is for the motor calculation. So next, similarly you can do it for the fault current, that is If double dash actual will be equal to If double dash per unit multiplied by I base. So now you already calculated this fault current in the step 3 If double dash. So that value we have to consider here. If per unit into I base. So I base is P base into root 3 V base. So here which base voltage you will take means, observe the single line diagram. So here fault is occurring on the near to the motor side. So that means you have to consider for the base voltage for the fault point is the motor value only, that is 11 kilovolt. Understood? So here the fault is occurred near to the motor side. So the base voltage we supposed to consider the motor value only. So now I have written the fault current formula. If value from the step 3, that is multiplied with P base by root 3 V base. You can consider the same value, 25 into 10 power 6 divided by root 3 into 11 kilovolt. So the final answer for this is minus J 11,232 amperes. So this completes the given problem. Thank you.